Greetings everyone, my name is Aniruddha Sanjay Devre. I am from Final Electrical from a student of MITWPU. I am going to present a topic, range estimation of electrical vehicle using MATLAB. So what we are going to do is we are going to model an electrical vehicle in MATLAB Simulink. It is a type of modeling that is physically available, means we are going to do the exact modeling as a physical model does. So what is a vehicle model? A vehicle dynamics model is represented such that it contains all the necessary aspects of making a real vehicle. Several examples are shown that such a model is useful as a simulation, as simulation observes it, dynamics phenomena can be recognized of simulation. The first step is adding and parameterizing the vehicle frame. So firstly we are going to add the vehicle body. Vehicle body has various parameters like the normal front force, normal rear force, therefore the angle, or therefore the slope or inclination, and the wind velocity, and and it gives output as v port, that is the velocity of the vehicle body. So the parameters of the block parameters of vehicle body are these all: horizontal distance from center of gravity, horizontal distance from rear axle, and this is the data that we are going to feed with the magic tire formula parameters. This we got from MATLAB Simulink Racing Lounge. This data we got from MATLAB Simulink Racing Lounge. Therefore, the step one is vehicle and tire modeling. After adding the vehicle body, we are going to add 4 tires to it and connect 2 tires to a single frontal or a single rear force. Therefore, there are 2 tires on the rear axle and 2 tires on front axle. Therefore, we are going to make a full car model. After that, we are going to add wind and terrain effects to check if the vehicle body and the tires are running smoothly. Therefore, we are going to give a speed of 1.2 meter per second square wind speed, and we are going to give an inclination of minus 30 degrees. Therefore, it will give a gradual increase in the speed for some time until the slope ends, and gradual increase in the distance. Therefore, this tells us that this is the vehicle body and the tires are in combination, or in combination with each other. Then the third step is adding brakes to the vehicle. Therefore, we won't give a wind velocity this time. We are going to add a loaded contact rotational frictional force, that is the rear force and the frontal force. So we are going to apply 2 brakes on the rear axle as well as the front axle. Therefore, the rear axle is there, front force front axle is there. Then we are going to add the angular velocity source, means the rear axle won't move on its own because we are not giving the wind or slope this time. Therefore, the angular velocity source means the rear axle won't move on its own. So we are giving an ideal angular velocity source for the rear axle to move on its own. And then we are going to apply brakes like 100 Newton at 58 second and 200 Newton at 75 second. Therefore, it will show us the front wheel slip, rear wheel slip, all this can be studied. Torque that is generated, we measured it on the scope, means the torque that is generated is also measured or is also observed on the scope. When brake force is applied, torque tries to regain its constant values again. So this is all the this is all the vehicle subsystems. We have the brake subsystem, vehicle subsystem, and the sensor subsystem. This is all comes in the vehicle body. So this is observed at 58 seconds. At 58 second, the 100 Newton force is applied, and that 75 second 200 Newton force is applied. Therefore, there are declinations or spiked declinations towards the downfall, and the distance constantly increases, and and it is observed the frontal increase or steps in front normal force and rear normal force. We are designing a single speed EV, means we are designing an EV with no gearbox, a single speed gearbox. Therefore, the power input is a DC motor. Then the step 6 is adding of powertrain block set components. So the powertrain contains motor, battery, and motor controller. So as it is a physical model, we are actually designing 24 cells and connecting them to parallel or connecting them to series. Therefore, means actual battery, in what happens in actual battery, we are trying to simulate the similar condition here. We are connecting cells in series and parallel and offering that storage to the DC motor to run the vehicle. Then we are controlling the motor using PWM average, that is we are using the parallel of controlled voltage source and controlled current source. We are using the PWM average. It does not give accurate values, but it gives fast value as compared to PWM accurate. Therefore, we are using PWM average. and therefore idle rotational motion sensor, we are sensing everything. Added motor to the vehicle. Now after the motor is added, we are adding a simple gear to it, a gear subsystem to it, and therefore we are trying to give a duty to it to see if the vehicle moves properly. This is the funnel model. We added a driver model here, that is a PI controller to and a PI controller to it, and this is a drive cycle source. It is a data is available in the Powertrain block set. So what this driver model does is it stores the values from, it stores or it extracts the value from this cycle and then gives the duty according to the drive cycle, and therefore the output is observed. So as you can see here, the yellow line at the back is the printed drive source, means it is what the input we gave, and the blue line overlapping it is our vehicle model following it properly. This is following it properly. So for example, if we give a WLTP class 1 drive cycle as input, so this is a input drive cycle for it to a driver model. This is shown as the output, means it is clearly identical, therefore our model is working perfectly. Thank you. So I'll just show you the model here now. So this is the model, as you can observe. This is the model. This is the electrical vehicle model. This is a driver model. This is our vehicle system. This is the vehicle subsystem. And so after simulation, it is seen this. So what our project exactly is: range estimation of electrical vehicle. As you know, WLTP class 1 cycle has 64 kilometers per cycle. Therefore running it for 10 times means we have a scope of 640 kilometers, but our vehicle is able to complete only 3.5. Therefore considering first three cycles, therefore it gives around 180 to 200 kilometers, 180 to 200 kilometers range for a vehicle. Now if we increase the motor capacity or the battery capacity, the range will increase. So this was a